What I'm going to talk to you about today is the biggest remaining problem with autonomous vehicles. And I'm going to talk to you about how people do it now, which doesn't work. I'm going to talk to you about why that doesn't work. I'm going to talk to you about how you, as humans, solve this problem. And finally, I'm going to get a little bit into how we think we can start to allow these vehicles to solve it the way you do. So this picture is it's not, we stole it from someone, I forget, but this is a depiction of how autonomous vehicles see the world usually. You have identification for all of the things in the world. You know what's a car and what's a pedestrian. You know where your street signs are. You know where the edges of the road are. You've probably driven this intersection, 100,000 times, and you've seen these boxes kind of move in different ways. And you use this set of information to do inference. You use this set of information to plan the motion of your vehicle. I'm going to take this view, and I'm going to superimpose this view on a real scene. So here's a real scene where we've kind of mocked up how an autonomous vehicle would see a real scene. And so that yellow box means that's a pedestrian. And you can tell that there's a crosswalk there. You can tell that the pedestrian is not in the street. And so if I asked you right now, okay, good, does that person want to cross the street? Probably. You could drive past here 100 times, 1,000 times, 100,000 times, and sometimes people would be crossing the street. Maybe mostly they would be crossing the street. And okay, so now tell me, does this person want to cross the street? And you wouldn't be able to answer it. As humans, when we approach this intersection, we have no problem because what we see is this. We see a person, and we see what they look like. We see them holistically. So this guy, look at him. He's looking at his phone. He's not going to cross the street. It's really obvious. So that sort of obvious inference is something that we as humans do effortlessly, and that if you just have a box, if you have an autonomous vehicle that's just rendering everything as moving physics objects in the world, is difficult, verging on impossible. This is sort of an interesting, there's a concept more of X paradox in robotics, that the things that are easiest for humans are hardest for robots or for AI. And this is exactly one of those cases. As humans, we struggle with the rules of the road. We struggle with, okay, what's the specific thing that I'm supposed to do in this situation? How do I learn to drive? As a 16-year-old, how do you learn to drive? How do you learn the different rules of the road in different places? How do you know which sign to look at? Maybe there are two it's confusing. It's challenging. Looking at a person and saying, oh, they're looking at me because they're trying to figure out if they can cross in front of me is effortless. And I think that very effortlessness has led to an undervaluing of the difficulty of the situation by people building autonomous vehicles. They sort of went from first principles, like, all right, well, what do you need to be able to drive a car or have a car that drives autonomously? Well, what do I need? I need to know where the road is. I need to know the rules. I need to be able to control the vehicle. I need to be able to understand what's a pedestrian and what's a tree. All right, we'll put all that stuff in. This further layer of social understanding is so transparent to us. We're so good at it that you really sort of don't notice it until you kind of start paying attention. And one of the fun things about giving these presentations is I think there's a reasonable chance that for at least some people in this room, I will break driving for you, because you will come out of this and you will be driving a car and you will notice how often you look at a person and you make a judgment about that person. How often you see someone standing by the side of the road and just glance at them for, quarter of a second and know all of these things about them. Oh, they're trying to get in front of me, but they're not going to do it. They're not crazy. They probably see that car over there. And so it's really, there's an amazing amount of understanding, amazing amount of inference that we are doing all the time, that these vehicles doing things kind of the standard way they're doing it can't do it all. It sort of isn't surprising that we're so good at this, because this kind of inference, this kind of social understanding is really what our brains, or at least a lot of our brains, maybe like 30% of our brains, have evolved to do. Our brains are this incredibly sophisticated, incredibly high-performance computing device, and this big chunk of it, like physically this kind of big chunk, most of it's in the front, but not all of it, evolved specifically to solve the problem of looking at another human and making judgments, making behaviorally relevant judgments about what's in their head. And this is kind of really different than computers have been architected. This is really different even in, a very elaborate hierarchical machine learning kind of environment. This is very different than how computers kind of naturally work. And honestly, there are people who are trying to sort of replicate this social understanding, right? Like putting together the building blocks so that they can have a computer system that can do social reasoning like a human does. And it's cool. It's a cool research project. It's 30 years out, 50 years out, and arguably when you do that, you build Skynet. So this is like, it's way off. It's really hard. It's as hard as general AI. It is general AI. But you need to do it for autonomous vehicles. You need to do it because these signals that we effortlessly use are the social currency of how we interact on the road. Things like, oh, this person is kind of holding themselves in a certain way. Oh, they're looking at me in this very intentional fashion. Oh, they kind of have some tension in their shoulders, like they might start moving. There's a great one that we found empirically. If somebody's holding a bag, we as humans are very attentive to how they're holding that bag. If you're holding it kind of loose on your shoulder, you're not going to cross. If you tighten up just ever so slightly, that means you're thinking, I'm going to start walking, right? Like I'm going to start moving. And you don't want your bag flopping around everywhere. And honestly, we didn't know that. Like we got that out of doing post hoc analysis of what our models cared about. It's pretty widely understood now in the industry that this is a huge deal. If you talk to Gil Pratt, who runs the Toyota Research Institute, he is very focused on this as really the central piece of the puzzle. Chris Urmson formerly ran Google's autonomous vehicle efforts, now the CEO of Waymo, also really understands this as the central problem. You can't solve it with sensors. You can't solve it with compute power. You can't solve it with LiDAR. You can't solve it by knowing exactly where everything is. And so it's really this central problem that's afflicting this industry, that's holding this industry back from actually having these vehicles exist and operate in cities, which is where their value pans out, and exist and operate in a way that they build trust, that they're useful to ride in, that they're not totally irritating to be around, and really that they work fundamentally. As an aside, I'm very fond of looking at the reports, especially from California, of incidents with autonomous vehicles. And one of the reasons I'm so fond of it is if you're kind of looking at it with the right frame of mind, you can see people getting pissed at them. So in particular, I think it was in 2017, the incident reports from Cruise, there were 2 or 3 times where somebody punched the car. Like, it just did something so stupid, and maybe they were crazy. It was in San Francisco, but it did something so stupid and annoying. I like to believe, because I've seen them do this, that the person just like up and hauled off and clocked the car. And this is a huge risk. Like, this is a huge brand risk. If these vehicles, when people first interact with them, are both incredibly timid and oblivious and cutting you off, then no one's going to like them. I'm not going to like them. So you really need to solve this. We do. I think that our thought is there's kind of one way to do it, and that is you need to take very seriously that humans, all of us, are the target, are the gold standard for this. You can't say from first principles, all right, well, how do I define the problem? What's an engineering solution? You have to really seriously understand how people solve this problem. you have to really seriously think about how you answer this question, these kinds of questions in a human-like way, without having to recreate, general intelligence. And the way you do that, or the way we do that, is by taking this process of studying humans, which you could call human behavioral science, neuroscience, experimental psychology, and taking those techniques and running them at scale, running those at a scale where we can use the result of human behavioral experiments, of studying humans, as the training data for machine learning algorithms. We take training samples, which are samples from sensors and vehicles. We manipulate them in order to make them, easier or harder, kind of get at different information in them. We show them to large sets of people. We ask people questions that are trying to get at not just, is this person crossing, is this person gonna cross, but getting at the sort of latent, unreflective, quick judgments that we actually make in the world. And then we have techniques for using that to train models that then can answer a question that's a little bit different than, where's that box going to move? The question is, okay, I want you to pretend there are 100 people in this self-driving car, and I want you to take a poll of them on whether that person wants to cross in front of the car. What's the distribution of their results look like? And so by doing that, what we end up with is an answer that without having, again, to build Skynet, reflects the kinds of answers that people give. And then that, because most of the work comes in how we collect our data, how we annotate our data, how we do this fairly laborious human behavioral experimentation at scale, the actual models we build can be lightweight enough to run on the kind of compute that's available in an autonomous vehicle. I'm just going to show you a quick demo here to give you a sense of this and how it works. What you'll see is two of our models. One of them is intention, and again, remember, this is, you have 100 people in the car, and you're asking, does this person want to cross the road? The other one is awareness, which again, you have 100 people in the car. Does that person know I'm here? It's worth noting, does that person know I'm here does not mean, is this person looking at me? Are they looking at me is easy, can you see their face? But if I'm like this, I can still see Jack. So you want to capture that kind of subtlety to it. And so you'll see, by doing our approach this way, you can get things like, well, this guy hasn't started moving, but before he starts moving, all of us in the audience and our models know that he's going to cross the street. This woman starts to cross, and then she starts looking at her phone, but she pretty clearly still knows the car is there. We can get that programmatically. This woman stops while she's crossing. This one's great. No, I gave away the punchline. So this guy, he's a delivery guy. He got out of his truck. He's walking parallel to the truck. He's walking parallel to the car. So does he want to cross, or is he going on either side? I think, honestly, it's ambiguous. And so what our model says in this case is, well, this is ambiguous. He could be crossing, he could be not. And then what you want to do as a vehicle is slow down a little bit and see what happens. In practice, this vehicle slows down and it's like, oh, thanks. Then he wants to cross. Then our model begs. This one, again, the woman in the blue skirt, she starts to turn, and actually as she starts to turn, but before she starts moving, her friend is kind of signaling to her, hey, we can cross. And you'll see this that she kind of spikes before she starts moving. And I think this one's pretty good. She's not crossing at a crosswalk. We can still get her. This guy, again, he's not moving. I'm kind of hurrying through these because the next one's my absolute favorite. This one. So think back to that diagram I showed you in the beginning. What you can get from that diagram, you can get someone's motion. Are they moving or not? You can get context. Is there a crosswalk or not? You can get historical data. Well, I've driven past here 1,000 times, 10,000 times. What has happened? What I love about this example is that this woman breaks all of those. She's not crossing in a crosswalk. She's jaywalking, so you can't use context. She comes to a stop. So if you're trying to extrapolate from her motion goes down to 0. So I guess she's stopped. You could drive past here 1,000 times, 10,000 times. This is a cab stand. everybody who walks out into the street here to a first approximation is going to be getting into or out of a cab. They're waiting for an Uber. But we as humans and perceptive autonomous models can say, well, look at her. She wants to cross. And in fact, she does want to cross. So these kinds of judgments, and then it works on bikes. Bikes are interestingly different. These kinds of judgments, these kinds of sort of intuitional kind of judgments are fundamentally necessary for these vehicles to work. And really the only way you can get them is by being serious about understanding how humans do it, taking humans as your gold standard. And as Brian Selesky from Argo points out, if you can't do this, if these vehicles are timid and stop and start and get punched and all of these things, autonomous vehicles will not work. Thanks.
Thank you very much. Very interesting stuff. Tell us a little bit about the company itself.
Sure. So we're about 20 people. We raised our seed funding from FirstMark Capital, and then raised an A round last October from Jazz Venture Partners, which is a firm that kind of specializes in neuroscience approaches. We have also have strategic investment from Toyota and Hyundai. We work with OEMs, so we had a partnership with Volvo Trucks that we publicized a few months ago, and with tier one suppliers, and with startups who are doing this. So really our goal is to take this module and sell this module out to everyone, right? This is something that is designed to be easy to integrate and designed to go into any kind of autonomous vehicle, and we want to sell it out to everyone.
And to the extent that you can talk about it, I guess, what is a roadmap for, in a year or 2 years from now? Because it's such a complex problem. Like, how do you know you're ready and it can be deployed commercially?
Absolutely. So the good news is it does what we say it does. So when I say, it answers this question, you have 100 people in the car, it does that. I think the next bit is how do we take that and make sure that answers the problems that our customers really care about, right? Because they don't care that we're answering that problem, they care that the vehicle drives correctly. And so what we're doing with our partners now, as we've kind of gotten past the first proof points of integration, is really making sure that we have the KPIs for, okay, well, this is what it should do for the performance of the vehicle. This is, you should have 10% fewer false positive stops without having any, false negatives where you run someone over. God knows. So getting to the KPIs and building out the tools around the core product that allows us to prove out the KPIs is really our focus right now and our customers' focus right now.
Thank you. One question in the back.
Great presentation. Thank you. Does it go as far as reading human expression? Because I imagine there's a lot of it's reading sort of how a person stands, but does it actually read the human expressions?
So implicitly, the way that we do this is that we want to capture every feature that people use, and so when we collect our training data, what we really want to do is kind of not have a strong prior, right? So if you use something like how someone holds the bag, okay, we want to capture that. If you use someone's facial expression, them kind of looking pensive or attentive, we want to capture that. And to get all of that stuff, you can't model it explicitly. If you tried to model it explicitly, if I sat here, and I've been doing this for years, if I sat here and wrote down a list of all of the things that matter for these judgments, I would miss the majority of the features that people use in an actual situation. So what we try to do instead is to use this toolbox from behavioral science to kind of without prejudging get people to use all the features we would use. And so one way to think about it is, well, What if you covered up their face? What would you use? What if you covered up everything but their face? And so you can kind of do these manipulations of the data and ask people questions about it. And then what you end up with is a training set for your model that that uses everything that people do. So certainly expression, but it's implicit.
Two questions. First is different people in different cities behave differently. So do you have to train different models for different cities? The second question is, how about dogs?
So different cities, absolutely. I think that the way that I think about it is there's kind of two components. Like there's the one component where we're just all people and we have a common kind of framework, but definitely there are cultural contingencies. And so what we've done is we've designed the system so that you can create new models without going through the entire process, but really by taking the kind of core model and then tuning it to different environments. But that's definitely something that we think about and that we do actively. Dogs, I don't really know what dogs want most of the time, I guess. I don't know. I feel like, so where we work really well and where this works really well is that when there's something where just inarguably everyone just knows what the answer should be off the top of their head. And I think with animals, that's a little bit trickier. Children, that's a really good question. So what happens with children, and this is actually, I'm going to lump in children and drunk people, because the commonality with them is they're unpredictable. And so really what you want the answer to be is, well, if you had 100 people in the car and you asked them, is that kid going to run to the road? People would be like, I don't know, but be careful. And so that's really the answer we want to get is if the situation is actually ambiguous, that's a really useful signal. You should be extra cautious. And so that's what the output does.
Similar question to hers. How do you control for outlier activity? Like if people are drunk, which a lot of people are, you cannot predict their behavior.
Yeah, so really what we want our answer to be in that situation is this is unpredictable. And that's kind of one of the downfalls, or one of the failures of the kind of physics-based approaches. In a physics-based approach, it's like, well, where is this person going to move? Sometimes the answer to that question is it's really unclear, and you just have to be very careful. So what we want to do is we want to represent the ambiguity when the ambiguity is something that people would see. And that's true for children, it's true for drunk people, it's true for, there's a lot of mental health services near our office, it's true for people that use those services.
Cool. Sam, thank you so much.
Sure.
Appreciate it. Great job.